Good morning, students. You are welcome to my channel. This time around, we shall be looking at a series on parallel circuits. Let's quickly look at what electric circuit is. Electric circuit is just a complete path provided for the flow of electric current. And simple type of this consists of a source of electric energy, that is a source of potential difference, and a switch to control the flow of current in the circuit, and the load or resistor in the circuit. Now, the word series and parallel describe how components are connected in electric circuit. So when we say series circuit, in a series circuit, all components are connected end to end, and there's only one path for the current to follow. And that makes the current to be the same at all points, that is across all components in a series circuit, but voltage is always divided across the components. Now, in a series circuit, if one component fails, other components stop working because current flows through one part. Let's quickly look at all this explanation. Now, looking at what we've been talking about, now this is an example of a series circuit. You can see the source of potential difference, and we have a load R1, that is resistor R1, R2, R3. The three of them, they are connected just across one path, and current that starts flowing from here, we just move straight like this to R1, straight to R2, to R3 without entering any range, because there's no branch across the circuit. So which makes the current that is in component R1 to be equal to resistor R2 and the one in resistor R3. That is what the statement is saying. And as the current is moving, as we have this complete path, if anything happens to any of these components, if any of them fails to work, it will definitely affect the remaining components, because it creates gap in this circuit, as if you've opened the circuit. That is one of the statements that we read before. And to now calculate the equivalent resistance across a series circuit, in as much that the current across the series circuit is always the same, that is, the current across all components is always the same. Considering Ohm's law, which is V equal to IR, in a situation whereby we have all the current across the components as the same thing, we can quickly look at that using that, because if the current are the same across and the voltage are divided, definitely the voltage across R1 will be V1, and that is I R1, and voltage across R2 will be V2, and that is I R2. The voltage across V3 will be I R3. Now, mathematically, if we try to factorize I from the right side of the equation, we can easily divide both sides with I, and we arrive at this. So this is the equation used in calculating the total resistance across a series circuit. That is, you add all the values of resistance together to have the total resistance. Now let's quickly go to parallel circuit. In a parallel circuit, the current split across branches. That is, there will be branches, that is, current will not be allowed to follow just a single path, and that makes the current that is coming from the source to be larger than the current that you are going to get across the components, because the current will be splitted at a point. Now, in a parallel circuit, if one component fails, the other will continue to work, because the arrangement allows electricity to flow through more than one path. Let's quickly look at this statement here. Now, this is an example of parallel circuit, and what are we saying? When current is coming from the source here at point 2 here, where we have a branch, the current can be divided. The current will be divided. One part of the current will come through R1, the other continue to point 3, where current will be divided again, and part of the current comes through R2, and here we have another current coming through R3, and that is what makes the current that is coming from the source here to be greater than the current across R1, R2, and R3. But summing the current across R1 and the current across R2 and R3 together, it will still give us the value of the current that is coming from the source. So that is what this equation represents, that the current from the source equal to the current across R1 plus current across R2 plus current across R3. And when all these currents comes back together to 0.7, they come back together to form the current I that is coming from the source. Now from this relationship, using Ohm's law, I equal to V over R, and dividing both sides of the equation by V, because V is the same across R1, R2, R3. Doing that, we have the equation below, and that is equation used in solving for equivalent or total resistance across the parallel circuit. Now let's quickly consider some example on parallel and series circuit. In our example 1, we have two circuits. And the first one is series circuit, while the second one is parallel circuit, but they're having the same value of resistance across them. They're having similar resistors connected across their terminals. Okay, now let's look at first one. In circuit A, we have a 10 ohm, 5 ohm, and 15 ohm resistance. If we are to calculate the equivalent resistance in this particular one, we are definitely going to add everything together, because in this circuit we have a series arrangement, that is, current is allowed to flow through one part from the source, and that makes us to add every resistance in the circuit together, and that is what we have here, and that gives us a 30 ohm. And let's consider the circuit B, where we have all the resistor connected in parallel. In this particular one, we know that the current that is coming from here will be divided across 10 ohm, 5 ohm, and 15 ohm resistance. So to calculate the equivalent resistance, we make use of this relationship, and that will give us the value of total resistance to be equal to 2.73 ohms. That is by finding the SCM of 10, 15, and 5, and solving that one. Mathematically, we have the value of total resistance to be 2.73, and from this calculation, these two calculations, we can deduce that in series circuit, the total or equivalent resistance is always greater than the value of resistance in individual components, while in parallel circuit, we have the value of total resistance or equivalent resistance less than or equal to the smallest of the resistance across the components. Okay, let's quickly consider example 2. In our example 2, we have the combination of both series and parallel components. Now we have resistor R1 equal to 5 ohms, and from the source, if current is coming straight from the source, the current that we have in 5 ohm resistor is still the same as the current from the source, but at this point the current will split into two. Part of the current will come into this loop, while the other continue to this part, and at this point again the current is will be divided again. Part of the current will come through 5 ohm resistor here, while the other one will come through this place. But at this point, all the current comes together and have the same value as the current that is entering this place, and that is what we are going to have here. Now, if we are to calculate the equivalent resistance here, first thing to do is to first calculate the resistance across the loop. I refer to this part as the loop. So calculating the resistance across the loop, we can now add it to this one that is in series with the source. Now, how do we calculate the resistance across the loop? Across this loop, we can see that R2 and R3, they are in series. So we add them together, 2 plus 3. So this gives us the value of resistance across this loop to be equal to 5 ohms. And also across this loop we have resistance R6 and R7 to be in series, so we can add the values together and we have 10 ohms. But this loop, this and this, they are parallel to one another, so it means we are going to consider the parallel relationship here. That is, the 5 ohms that we have here and the 10 ohms that we have here, they are parallel to 3 ohms resistor, 3 ohm resistance and 5 ohm resistance. So in doing that, we can easily carry out our calculation as it is done here. Now, for the resistance across R2 and R3, we have this, and for the resistance across R6 and R7, we have this, and this R2, 3 and R6, 7, they are parallel to resistance R4 and R5. That is why we use the formula for solving for equivalent resistance in parallel here. So using that, we are able to substitute all the values into the equation, and we arrive at 1.6 as equivalent resistance across the loop. 1.2 ohms as equivalent resistance across the loop. That is the equivalent resistance across the whole of this loop equal to 1.2 ohms. Now remember that the entire loop here is in series with this R1. So using that, that's why we use the series relationship, and we are able to add 1.2 to 5, and that gives us 6.2 as the effective resistance across the entire circuit. And lastly, we are looking at cells in series and parallel. When like other components, when cells are joined end to end, they are said to be in series. That is, when we connect their unlike terminals together, that is positive to negative terminal, when they are joined together, that is when we say cell is in series. And once they are connected in parallel, that is when we have the like terminals joined together. That is when positive is connected to positive and the negative is connected to negative. That is when we have parallel connection in the cell. And what is the effect of this connection in the cell? When cells are connected in parallel, the value of equivalent voltage or potential difference across them is equal to the value of one of them. For example, consider the diagram in the first part of this, the first diagram here. When batteries are connected in parallel, we have cell 1 having 1.5 volts, cell 2 having 1.5 volts, and cell 3 having 1.5 volts. But the combination of the three in parallel will only give us 1.5 volts because they are connected in parallel. But contrary to this, in series combination, when we connect cells in series, the equivalent potential difference across them will be equal to the sum of all the individual potential difference in each of the cells, and that is why we have a 6 volts for this series arrangement, because each of them is having 1.5 volts, and combining these together we have 6 volts. And you can see the diagram of parallel connection of cells and the series connection of cells as well. So that is with that we come to the end of today's topics. In case you have any question, please you can drop your question in the comment section. The question will be attended to. And if this video has added any knowledge to you one way or the other, please try to like the video, and please click a subscribe button so that whenever we have a new video you will get notified. Thanks for watching.